So remember that the uncertainty principle, it all has to do when the basis set of an operator, and now you know how important that is. When you have an operator that's the answer to your question, it can't be answered without its basis set, without its eigenvalues. The basis set is the complete set of eigenfunctions. Eigenvalues are the answer. So you gotta have that. If you don't have that, you don't have anything. So we're just gonna presume you have that, using all the mechanisms that we talked about at the beginning of the class, and then we're actually gonna get back into it. We're gonna solve the eigenstates of the harmonic oscillator. We're gonna solve them by hand. So again, you're gonna get immersed in that. All right, the problem is when you have a different operator and when they don't commute, the basis functions of one operator are not the same as the other. And maybe while you're cool with one of them, you're not the other. And for whatever reason, your research, you need to know them both. Now, there's some slick solutions to get out of the problem. Sometimes there's not. But just like you can, okay, in an NMR, I want to know where the nuclear magnetic moment is pointing. And I can point it up, all right? So I know that because I can put it in the magnetic field. But now I want to know X and Y. Well, that's one of the ones that there's actually really nothing you can do. But you can build, but so what? But now I know how to build a Fourier transform NMR. So win, right? So uncertainty principles do things. Now this is the statement of the uncertainty principle. Again, if you have the commuter 0, then there's no uncertainty principle. But if not, there's this, and here's a relationship between the variances. So of course, variance is the statistical measurement of uncertainty. Okay, now I started out just doing something really kind of bizarre. I just did an overlap of a state defined this way. Linear combinations of states are states themselves. There's nothing weird about that. I had this lambda. You're going to play around with this on the next problem set, by the way. When I look at this, at alpha minus lambda beta, what the hell is that? And then I got this crazy ass lambda. What does that mean? All right, again, in the next problem set, you're going to play around with this and you're going to see why it's meaningful, but let me just look at it. Okay, well that's the norm. Beta overlap, that's the norm. So beta is normalized. Okay, sure, beta is normalized. This is the overlap of alpha and beta. So what I'm seeing here is the A state without any contribution of the B state. Anyway, and what does that do? I don't know. I'm just saying is that it's not just a bunch of squiggly lines that have absolutely no interpretation. I can interpret this. And so what? Okay, the overlap, after some manipulation, just one or two steps of Dirac notation algebra, you got to here, and then you just multiply through by beta, rearrange, and now you get this. Okay, now notice how close we are to this and this. It's so close and so far. Okay, so where is the operator? Okay, so oh yeah, look at that. There's two things. There's two things here, but that's an operator and that's an inner product. So where the hell's my operator? All right. So it kind of looks the same, but it's not the same. Okay. Or where's my operator? Where's the commutator? Where the hell's the commutator? So close yet so far. All right. Now again, we did this last time. I just want to again walk you through this. One of the tricks, I know it's a slick trick, but it is it is totally fine, is alpha was never alpha and beta was never beta. Alpha and beta were actually the result of operators. So operators, remember, they turn a ket to another ket, and they spit out a value. Now, maybe it's the same ket, in which case it's an eigenfunction. Maybe it's not. The eigenvalue could be a number, could be 1, could be h bar, could be 0. It doesn't matter. I mean, I'm not saying what alpha and beta are, which is the strength of this thing. And it means I have incredible flexibility. I can define, secretly alpha was actually this. The only thing that this could go crazy on you is if these operators were like automatically 0, and they're not. In fact, I doubt they're ever 0. Okay, so with this, again, another slick willy trick. You're able to insert the operators, the variants of the operator. There you go. Of course, see, there's one on the one for the ket, one for the bra, hence the square of the operator. I believe we're assuming they're Hermitian, and so that's why the transpose operates on the bra, but the transpose is equal to itself, so that's why I can do that. I have to double check that though, that it's defined as Hermitian. You may notice I'm also missing the 1/4. I'm missing the 1/4. Right? I haven't found that yet. No. Okay, so now where's the 4th? Commutator, still not there. Okay. We got way closer here. Now we just gotta figure out where's the 1/4 and where's the commutator. Okay, so that's where we were at, and I had to stop then because that's class is outside waiting. Okay, and then the trick was that now I wrote this down, so I'm just going to go ahead and assume that it's in your notes. This is not a proof. This is not a proof. This is just a algebraic fact. So you remember, again, because I'm in danger of not prattling on way too long as I always am. This is 1/2 AB plus 1/2 AB minus 1/2 BA plus 1/2 BA. Anyway, that should be in your notes from last time. So remember, this isn't some crazy proof. This is just 1/2 X plus 1/2 X plus 1/2 Y minus 1/2 Y is X. Right, so again, that was in your notes. Okay, now this is the one last step that's funky. Last step. What I'm going to now do is take the absolute value. I'm going to take the absolute value of the square. Sorry, what I need to say is I'm just going to take the absolute value, which is the square. Be a little careful on MATLAB. MATLAB has two different absolute values. One is the complex conjugate times the number square root of, and one is complex conjugate of the number times the number. In other words, they differ by taking the square root or not. Anyway, you're going to be doing some stuff with MATLAB. Okay, now this is where it gets strange. Watch this. All right, now I'm going to have to FOIL this out, right? Okay, but I'm not. Watch this. Now, this part is not hard to imagine. And here you see the commutator, right? So you see me introducing the commutator, and you see a 1/2, and that 1/2 is now squared. So I've taken the FOIL, I've done the first term. Okay, let's you got to use your imagination now. Let's do the last term. You notice that I got a commutator in the 4th, right there, 1/2 squared. And as I was also telling you, the anti-commutator, I never seen anti-commutator except in the proof of the uncertainty principle. I have never seen it used anywhere else except here, but here it is, and you need to know. So there you go. Okay, now for the OI of the FOIL. Nope, not doing it. Took the first term, took the last term, inner outer. No inner outer. Watch this. Okay, this is an aside, but I want to write this down. Okay, so let's do this. A times IB, A plus IB. Now, I'm going to do the complex conjugate because, of course, this is, right? We all agree? What's this equal to? A squared, okay, inner and outer, B squared. Huh? No, that's it. No. Right? Yeah, I think some of you said, keep going. No, no, no. That's just A squared plus B squared. Guess what? Real? Imaginary. That's A. This is B. So I don't need to go further. This is the answer. Since this is always imaginary and this is always real. In other words, Hermitian. Anti-commutators are Hermitian. Commutators are anti-Hermitian. I will prove that. Okay. All right, now I'm just going to keep going, and I'll prove that in a minute, but whatever. Okay, now this is it, by the way. I do find this kind of interesting. Therefore, you can say, okay, again, we've got the left side of the thing correct. What you're going to do, you're just going to cut it. Just cut it. Let's bring out the fourth. 1/2 squared. Oh, so actually, I said that this is the end. It's not the end. I've got two more. I've got one more thing to show you. And then I'll show you commutator versus anti-commutator. Sorry. Do not forget any of this bracket, dash, delta, and that bothers me. It needs to be bigger. Okay, bracket, less than sign, I guess. There we go. Okay. Notice this is kind of wacky. You simply, I mean, yeah, this is everything's squared, so everything has to be real and positive. So if you're simply going to shave off some portion of a number, then the left side has automatically got to be bigger, right? It's an absolute reality. So the fact that everything is, I think the math term is definite real or real definite, just it's really positive. It's definitely positive. Actually, I don't even know if I'm saying that right. Anyway, okay, so there you go. All right, now, I said I thought, hey, I'm done. I'm not done. I'm not done. I made a mistake. I haven't made a mistake. That is delta, the standard deviation, right? This is the standard deviation of the commutator. It's supposed to be the commutator, right? Remember that delta A. Okay. Now remember, I've got, I mean, it looks like I'm there, right? It's like I'm done, except I've got deltas, and I actually need to have no deltas. Okay, so there's one more step to derivation. All right, maybe let's see if I can put it here. Definitely wish I had a better room. Okay. Turns out. Damn it. What's it here? Okay, delta A. All right, this is quite a mistake. I think I need more room. Delta A, delta B, minus delta B, delta A. Okay, now here's the trick. And don't forget that this is what Yes, standard deviation. Just call it standard deviation, because the square is the variance. Square of the standard deviation is the variance, right? Now that I know is correct. Okay, big picture. Now clearly I'm going to show that this is equal to right? So what I'm going to show is that the standard deviation is just equal to the operators by themselves. So this is where I'm going with this, right? And then if I put that in here, then I've got the uncertainty principles worked out. Here is how you got to be seeing the big picture. I know that this is going to work. For one, it's in my notes, it's in the book. Number two, all right, the problem with commutators is AB is not equal to BA, right? If you permute the order of an operator, it doesn't give you the same result, right? You change things by measuring them. That's the big picture. And if not, you don't have an uncertainty principle. If AB is equal to BA, then there's no uncertainty principle, and why am I even doing this? Right? And there's a lot of things for which that's true. Okay, but we're going to assume that AB is not equal to BA. Operator. However, the only thing that makes this standard deviation is that I'm subtracting the average value, which is a number. Okay, 5 times 3 minus 3 times 5, well, that's going to be 0. All right? So I can tell that this is going to work out just fine. Okay, so let's drop that. Okay, so what are we going to get? We're going to get A minus average A, B minus average B, minus B minus average B, A minus average B. Okay, yeah, you see, I really should not be doing this here. I'm running out of room. Okay, so that's what it is. Now, I will be very careful about going in order. A, B, this guy needs to be in front. All right, now, when it comes to a number, though, when it comes to a number, I'm okay. So, I can put the number anywhere. Okay, so there's that one. Okay. Minus the brackets. Oh, it's missing a hat. There we go. BA minus. I'll do this one. So I'm going slightly in different order. Doesn't matter if it's a number. Now I'll do this one. You can't look out that I've gone into different. Oh, in bracket. Okay, and this is the AB minus BA. BA minus BA gone. Minus AB plus AB gone. Plus minus gone. Commutator. There you go. All right. And that's it. So, so let me wipe this out. I'm doing that for convenience. Don't do that to your own notes, okay? I'm doing that because of I don't have room on the board. There you go. That's it. Except for this, the whole thing I just did. There we go. Last step, which is the first step. All right. That brings me to one last thing I want to point out, folks. When you're doing homework, please, I almost have your homework grade, but you're fine. Please try, like, when I give you an answer, some of you are working in reverse, you're reverse engineering it. Please don't do that, all right? I mean, I'll count it as right, but it's just that what if I didn't give you the answer? Remember, I give you the answer sometimes so that you don't get completely frustrated and go barreling in the wrong direction. But some of you, again, you're reverse engineering it. You look, I'm doing you a favor by often giving you the answers to homework. Don't use it, okay? That's kind of cheating. Anyway, so I did that here, right? Now remember, I was not reverse engineering. I started here and I ended up here at this last final step, right? So I did not reverse engineering. Okay, so there you go. Last bit is the anti-permissivity. Now we've done Hermitian. We did that a while ago. Hopefully you remember. I'll do anti-Hermitian just for the heck of it, and then we need to move on to basis set transformation. And as usual, I'm still too wordy. And also remember, you're actually, this proof, you're going to be doing a lot with this on the next problem set. So you don't need to memorize it or anything. But, okay, so, what am I? Okay, so I want to prove that delta A, delta B is anti-Hermitian. Okay. Now, what that would mean is, and one thing that's also kind of interesting today is, I've just proven that the delta is the same as the operator. So, so I'm going to drop the delta, just less to right. Okay, so don't get confused. I just dropped the delta, but obviously that's okay. Okay, now Hermitian means that an operator is equal to its transpose. Where transpose is not something I've really defined yet. There's nothing to define for a Hermitian operator. Almost everything is Hermitian. So cool, there's nothing to talk about. As we get into more operators, and you're also, the operators you're working on the last two questions, those operators that you have to figure out, those are those are not Hermitian. So we are stepping into the world where we need to know what transposes are. As I mentioned before, I know you just want to make all the i's a complex conjugate. That is a conjugate, not a transpose. Transposes are not conjugates. What are transposes? It depends. Every operator is different. Now, for the most part, again, the transpose is the operator. Non-Hermitian ones, that's not true. What are they? It depends. Every case will be different. So, anyway, but I do want to point out, for an anti-Hermitian, we're going to have this property. So remember that, I just wrote minus itself, right? So the transpose will be minus, so the operator is minus itself, right? Equal, opposite, right? So that's all it comes down to. So anyway, I did this, so notice a commutator is an operator. That's still the operator, so I just took the transpose. And to make sure that it's a number, right, I can't, it's not very sensible to say that an operator is minus itself. I want to make it a value, so I'm doing the absolute value. It's going to make this a lot more clear. To be blunt, this is what makes the proof work. Okay, so let's, so I'm going to work with simplified notation. Let's do this. notice that okay, but you know what I did? I did a step. I did 2 steps at once. Let me not do that. Let me not do that to you because it confuses. It's very confusing. There we go. All right. Operator. Now again, remember, when the operator, if you want to act on a bra, the trick is to flip it, right? Operators generally, they make sense to operate on their ket. All right, so if I want to operate on the bra, I might want to just flip the whole thing. All right, that's why I did a complex conjugate. But now again, now I'm wanting to operate on the bra, so now I need to deal with the complex conjugate. The transpose. All right. So the point of a anti-Hermitian is that now the operator is back to its normal self. It's not the transpose. Well, what I do is I pick up a minus sign, so that's why it's okay. Right? And if this was Hermitian, then there's no minus sign, it's a plus sign. Okay, so I know it's a bit of a mouthful. Okay, now again, remember that a operator generally likes to operate on its ket. So I would say that is an eigenket of the operator. So it spits out a number, and leaving an inner product, which I don't know what it is. Okay, let's look at this SOB. Okay, so I'm going to have this operate on the ket. Everything's a complex conjugate. Leaving alpha beta, complex conjugate. Okay, but I would like to factor, I'd like to bring this over and factor the inner product. And I can't really do that as it stands, so I'm going to have to just flip it over. And that means that you also don't have a complex conjugate. Okay, a little bit of algebra, where I've got alpha plus beta complex conjugate. So when you have an inner product to the complex conjugate of the inner product, whatever gets gutted out, like the operation, is still a complex conjugate. That's why that's okay. Then I've got alpha beta. All right, now alpha beta. So what if?
Wouldn't it be beta alpha?
Yeah. Sorry. Yeah, I'm sure my notes are beta alpha. Yeah, my notes are beta alpha. I just writing off the top. Thank you. Okay. Now the trick is, remember, I didn't define. You may recall when we did Hermitian this and that. I never said what alpha and beta were, so they could be the same thing. If they're the same thing, this would be 1. Assume that it's normalized. 1 is not 0. So when is a number equal to minus its complex conjugate?
It's imaginary.
Yeah, it has to be pure imaginary. Right. 3 is equal to the complex conjugate of 3. 3 equals to 3. Well, that doesn't cut it. It's not minus itself. 3i, complex conjugate, is minus 3i. So it's equal to minus its complex conjugate. But it has to have an I in it. Therefore, it's not just imaginary, it's pure imaginary. Right. We say it's complex. If it's complex, then it has a real and imaginary component. But if it's pure imaginary, the real component is not present. Okay. So there you go. I actually have run into this one before. I have run into the fact that commutators are anti-Hermitian. I've seen some talks where that was actually important. So you might see that again. Okay. So to summarize, there it is. Have fun on the next homework where you're going to manipulate this. What you're going to do is you're going to work with a particular type of wave function that has the minimum uncertainty, and that's when the uncertainty principle, instead of being greater than 1/4 the commutator, it's when it is equal to 1/4 the commutator. It's called a Gaussian wave packet. You will hear that ad nauseum in talks. Gaussian wave packets, which you are going to spend half your next problem set on. You're going to derive it, and then you're going to use it. Gaussian wave packets are wave functions with the minimum uncertainty. They're used all the time, and they're never really explained very well, but that's, anyway, you're going to see that again. And you're going to do that by solving, you're actually going to solve a differential equation. What you do is you set up the uncertainty principle, spread in A, spread in B, equal to 1/4 the commutator, not greater than 1/4 the commutator, equal to 1/4 the commutator. And you're going to set that up as a Diffie cube, and you're going to solve what state, for which state is that true, and you're going to get e to the minus x squared. That's how it's going to go. Just so you know. Okay, gotta hurry here. This one's important. That last question on your homework, I wasn't fooling. I had to do this a month ago for a research project. I had to do that transformation. Now it's also, I hope that you find it kind of neat. The last question, if you haven't seen it, is you have to think about molecular orbitals like S, Px, Py, and Pz. Right? So that's almost everything, except transition metals. Most things are bonded through their S and P orbitals. Px, Py, and Pz. No, that's fine and good. Okay, but you actually need to work in a basis of sp3 hybridized. So you have to transform a matrix that works in Px, Py, and Pz, and you have to transform it to sp3. So that's what we're doing here, transforming a basis. So now you can kind of see a little bit more, again, like why is this actually useful? So that's why that question exists. Now, it's also true, now you need to do this for uncertainty systems. Okay, if one reason to work with a different basis, again, actually I have to defer to my problem set. As you read the book, it just says, hey, let's do this in a different basis. Why the hell would you do that? Look at the problem set. I give you a reason why you might want to do that. So it's actually the best example I can come up with. Which I think is like one of the best examples. I'm really praising myself on this. I shouldn't, but I am. I'll give you a really good example about why you actually do want to transform the basis. Now, of course, and it would have to do with, when you have an answer for one question, but you need the answer to another. And again, you'll see why on the thing. Okay, now to do this, let's talk about alpha, state alpha, which I don't know what it is, which is the sum of states in the A basis. And of course, we know that these expansion coefficients are the overlap with a resolution of the identity. This is remember how you resolve an identity. You resolve an identity in front of this. And so how much of the state projects into any eigenstate of the operator. And of course, you may have an infinite number of these. If we're doing spin, it'll just be up and down. But if we're doing anything else, it's probably an infinite number. So that works. Okay. Now what you want to do is this. Now you want to solve the state in the B representation. Now again, A goes with A, B goes with the B operator. If B's commuted, this is stupid because the A kets and the B kets are the same kets, right? They have the same eigenstates if you commute, but these don't commute, these states are not the same. So P px, py, pz, s, px, py, pz are not fundamentally the same as sp3. And by the way, you have 4 states, s, px, py, pz, that's 4. And then I said sp3, well that's 1. Right? Right? That's wrong, that can't be right, because that has to be 4. sp31, sp32, sp33, sp34. It's inherently tetrahedral. Tetrahedrons have 4 vertices. There you go, that's why there's 4. 4 and 4. Okay. Blah, blah, blah. All right, now, what you're going to do is you're going to transform with the unitary operator. Sorry, U, and which is a unitary operator. And unitary means U times U transpose. It doesn't matter what order you put them in. I think I'm just copying from the book. An operator times itself is 1. Now, of course, we're going to be using matrices. That means the identity matrix. Notice that now you actually have a definition of a transpose for the first time. You now have some idea what a transpose can be, but only for unitary operators. There's so many other, there's projection operators, there's Hamiltonian operators, there's momentum operators, there's unitary operators whose job is to transform basis. Momentum operators, transposes are the same as the operator, they're Hermitian. Hamiltonian operators, the transpose is the same as the operator, it's Hermitian. This sucker is not Hermitian. Absolutely cannot be Hermitian if it's going to transform A to B. There's no way that's Hermitian, right? It has to kick out the same state. Anyway, I'm rambling. Now you have a definition for the transpose. And by the way, on MATLAB, what you do is you have a matrix. So you have a matrix, so what you do is do this IMD. Once you have a matrix, inverse matrix is the T-mat, transpose matrix. Call it what you want, right? Anyway, so now you're able to actually do something with this, right? Now you can really see what a transpose is for this circumstance, and you can define it. And you're also going to be writing your matrices. Okay, so what is a unitary matrix? Now let me forewarn you. There is one thing that is funky as heck about this. I'll use the same notation as the book. We'll be transforming between A and B. Okay, it's an operator, so it better look like an operator. An operator is come in the form of cat bra. Bra cats are inner products. Okay, let me go ahead and warn you. The challenge, the thing that's a bit of a pain in the rear end about these unitary transformations is that U is the one that is easy to kind of just figure out. So like you're going to be transforming like spin up Z to spin up Z, to spin up X, right? In your homework, you have to figure out the unitary matrix that transforms the spin up in the Z form to spin up in the X form. You can just stare at it. It's a 2x2 matrix. You can just stare at it and figure it out. I mean, it's really not hard to just figure it out. Okay, but warning, this is the one that's more important. It's weird. This is easy to figure out, but you actually need to know this one. Heads up, that's just how it is. Now they're proven. Okay, now you may notice that, of course, if you put these two together, you're going to have A cross A, which is a delta function. Let me do this just so you get, and I'll write this in a different order. It doesn't matter what order. Notice that I just switched labels, and I'm doing this because the labels are arbitrary. There's nothing magic about the K's I wrote up here. Yeah. Now you get a Kronecker delta for KL, and you end up with, now you just have to decide which one you're going to switch. I'm going to switch K. Sorry, I'm going to wipe out L. I could have wiped out K. It doesn't matter. It doesn't matter which one you pick, but just pick it and stick with it. Okay, what's that? How do I show that that's 1? What do I do?
Solve it.
Huh?
Solve it by putting that.
I think I'm actually already done.
Sorry,
It's a resolution of the identity, right? It's a purely diagonal matrix where all the elements are 1. So remember, the way you represent this in matrix form, here is the here's the operator, and here is the 1, 1 element. What 1 times 1? 2, 2. 2, 2 would be this. The only number that survives of the sum is that. If you have any off diagonal, well, that's 0. If you're off diagonal on the other side, that's 0. Right? That's 0. There you go. Resolution of the identity is 1. Cool. Okay. Next bit is we're going to want to write So note that I know what alpha is in the A rep. All right, I've already done this. Remember that kets should be column matrices. So what I need to do is figure out this, right? So because now I'm writing the ket in the B matrix. Okay, now here's the deal. I've got this already. Right? This is the nature of the problem itself. I already have this, but I need this. So again, for all the reasons I just said, you need that, but you're working in the A rep. So what do you do? Okay, real quick, and I'll end just slightly out of time. Okay, now in the A rep, alpha, and I'll use the letter L. That is A, by the way, not alpha. Okay, then B. Okay, now when I put a dash, here's what you need to be thinking. I'm building the rows of the matrix. Okay. So again, there's not much to that. But now what I'm going to do is do this. Now remember that the bra B is going to be going to come from A. So to turn into D, we need the unitary matrix. But notice I'm operating on a bra, so I need the transpose. Remember, a minute ago I said the transpose is actually the most important, but not the first one you're going to derive. Generally, you derive the unitary matrix, not its transpose. Okay, so what you end up with is now, real quick, and we're in just a minute or two late, let me show you where this is going, and then we'll wrap up the details next time. When you look at the problem, especially not the last one, but the next to last one, you'll actually just be able to figure this out. Okay, so remember that I've done this enough times, I hope you're okay with this, but So normally you would have, right, in the A basis set it goes on and on and on, but what you really wanted to do is the B, right? Now the reason, so let me turn these dashes into actual numbers because then you can see where the number of forces represents the eigenstate. We assume that there's an infinite number. So here's how this is going to work. I'm doing the diagonal because that's always easy. And of course, then I remember, now remember, I'm actually drawing, these are different. Run. And here's what you know to do. Now, of course, what's good to do is to spin up, spin down for like SE basis set. Here's your 2x2 matrix that you're going to figure out on the next to last problem. And then here's your, and then here's the new representation. So you're going to be taking things in SZ and you're going to be turning them into SX. And to do that, you have to figure this out. You know, all right, so again, you're in the SZ basis, which is awesome. SZ is easy. You just have to figure out what the U's are.